Welcome aboard, everyone. Hope you're enjoying it so far. I'm very pleased to announce this session is all about capacity. It's when reality derails capacity planning for Db2 zOS. And I have Michael Bieleczki from the SWAT lab or the SWAT team in Db2 zOS and IBM. He supports, advocates for customers across various industries and geographies. And prior to that time, he was a system stroke application DBA and a customer, and for the last 18 years. So very pleased that Michael can join us today. And I think as long as you can remember that we have the chat open for questions, and we'll try and get questions in along the way. The session is being recorded, so hope you've all accepted that that's okay. I'll hand over to Michael and we'll press on. Thanks very much.
Thank you, Colin. Can you hear me okay?
Loud and clear.
Okay, thank you so much. So thank you very much for joining. It's a great honor for me to present at GSE Virtual Conference this time. So my name is Michał Białecki and I'm working for Db2 zOS SWAT team since 5 years. Earlier I was a customer, I was also the support person, so you may recall my name from the PMRs as well. I kind of feel strange because I have two displays, so I will turn off my monitor or record, well, the camera, so you can not see me from the, sides. Anyway. Okay, so this session would be about capacity for Db2, for the aspect of Db2 as well. If you have any questions on the way, please don't hesitate to put it in the chat, and I hope that Colin will help me with noticing them, because when I'm presenting, I don't notice. So our team in the SWAT team, what we do on a daily basis is Db2 360 studies, also known as the health checks. So during those investigations that we do for the customers, we also do the capacity setup check for Db2 and how Db2 overall and applications are running. So this presentation gathers those experiences. So those examples that I have put here, of course, are anonymized, but they are from the live customers that we studied in the last few years. So we know that ideal world does not exist, right? And nowadays, everything is ruled by money, right? And in ideal world, the capacity shall be the reflection of the business needs, shall be the reflection of the agreed service level agreements, right? However, the reality is that we often meet situations where there was indeed some SLA long time ago, but from that time, the workload has grown, or there was some organic growth, and SLA is not met, and the hardware didn't change, right? And due to the cost savings, there was no added capacity. So someone is still trying to fit 2 liters into 1 liter container. So capacity planning actually should be continuous work. So we don't hit the wall the one day, right? But if we do hit the wall, if there is not enough capacity, this can cost us a lot, right? And actually, this also can be an eye-opener for management, right? Because then they ask a question, right? How much money we lose due to the system sickness, right? How many customers abandoned their purchases, for example? Or how many customers lost the confidence, right? Or in some areas, for example, are we in danger of losing banking license, right? Because our system is not available for longer than, let's say, 2 or 4 hours, right? So there was a famous saying by my former boss, John Campbell, which was leading the SWAT team earlier: never waste a good outage, right? So that means that it's a last resort, but it actually can work. There's nothing speaks so well to management as money. The money they lose, right? So never waste a good outage. That's the theme for this presentation, let's say. So in my agenda, I will cover 3 aspects of capacity planning for mainframes. Generally, I will speak about the general CPs. I will speak about the zip assisting processors and memory real storage. So let's start with the general CP. How CPU capacity shall be evaluated, first of all, right? Actually, the easiest to evaluate is basically by pain. I mean, what is the design objective for CPU busy? What percentage of CPU busy is affecting your business, right? When your transactions are slowing down, is it 90%, 80%, 85%, 99%? What is your, let's say, objective when you start to worry, right? When your phone starts to ring, right? Or for example, when your batch is not meeting the deadline before the online day, right? Another way to evaluate the capacity is about, predicting the peaks, right? Are there any days when you expect more workload? For example, Black Friday or before Christmas, right? Are there any reasons why you cap your workload, right? Are you capping your workload due to the cost, right? You want to save some money, right? Another aspect of capacity planning is what do you do if you need to adapt the failure of a keg, of an LPAR, or Db2 member? How quickly you can add capacity if you have the spare capacity, right? And I already mentioned about the cost, right? How much capacity lack can cost you, right? So that would be the main drivers, how CPU capacity should be evaluated, and overall, all the capacity, right? So in general, capacity should be planned this way. For safety, not more than 95% CPU busy. At least you should have one general CP, which is not occupied. So it also depends on the numbers of processors that you have. If you have 10 processors, then your target utilization should be no more than 90%, right? Otherwise, if it gets too busy, if the mainframes are too busy, and I know the customers who are running 99% busy, you can pay some performance penalty due to all the hardware being busy, right? Because the workload gets dense, all the buses, all the, let's say, connectors inside mainframe get busy, and it basically slows down. Why it matters, this CPU utilization? It matters for the cases where there is no much workload that can be sacrificed, where we have all the importance workload and we don't have the workload that is non-important. And when there are peaks, we cannot sacrifice any workload that is lower importance, right? So if there are any delays for our important workload, they may cause also sympathy sickness. For example, if we are having the workload that's running slow and it holds an important lock or latch in Db2, then it, of course, takes longer for this guy, but it also may slow down the others because the others will be waiting for this lock or latch, right? So we have some cascading effects. So we call it sympathy sickness, let's say, right? And the same thing about the capping, right? When we have the capping, it can also cap the workload that we want to cap, but it also can cause sympathy sickness for the others that are waiting for the resources by this guy who is delayed. So the first example here, what is wrong here, right? We have the system here. We see this system has some service classes, importance 1, 2, 3, 4, 5. And we see the system very often hits 100% busy. But that's not the end of the world, just hitting 100% busy from time to time, right? The end of the world may be that majority of this workload, as you can see, is importance 1, right? So majority of the workload is importance 1, which is this gray area, right? Or system sysstc, right? So basically, if importance 1 workload will have some unexpected peak, if we have more traffic than we expected, right? There will be very little to give because the only thing that we can give are the lower importance classes, right? Which may be here like 10% only, right? So that's very, very dangerous situation, right? On the normal day, it may be okay, but if you have the peak and there is higher demand for CPU for those high importance classes, then you are in trouble, right? So either what you can do here, either you can really distinguish between the important classes and non-important classes, or the other solution here would be to add capacity, right? Okay. I would like to also talk about the catch that we also sometimes meet from time to time and misunderstanding here. I already mentioned about performance penalty as soon as CPU gets busier, let's say, right? Based on measurements that IBM did and also other vendors, actually it applies to other machines architecture as well. With every 10% increase of workload, there is additional 4% increase for existing workload. So this means that if machine gets busy, and if we add some workload to the machine, the workload that is already running on the machine will get slower too, right? So if you look at this picture closer, right, here's the CPU busy, you can also notice that at the end of this line, when we are close to 100%, this factor is much higher, right? Basically, the closer we are to 100%, the slower we will get, right? The less capacity we will get, right? This is due to the fact that the hardware has its own capacity bottlenecks. It's like a highway when you drive with a speed limit of 100 kilometers per hour. The more cars on the highway, the more congestion we have, right? So with adding some more cars, we adding congestion also on the mainframe, let's say. So you need to basically adapt this to your capacity planning, right? And I will talk on this on the next slides. So this brings three implications, right? This growth. You may have less headroom on your mainframe than you think. That's the first thing, right? Because you may think that you have enough to adopt some more new workload, but in fact you have less than you think, right? So for example, if you have mainframe or a LPAR that is 50% CPU busy, and their workload is running, let's say, it's a 1000 MIPS workload. This means that you don't have capacity of 2000 MIPS on the full LPAR when you run 100%, but a bit less. So to adopt another 1000 MIPS on top, you would need at least 20% more CPU. Basically, to run the 2000 MIPS workload, you will need, let's say, 120% of what you already have, right? There is another thing. If you are adding capacity, if you have to add a capacity, you should be doing this at the very first sign of being a little sick to prevent congestion. Otherwise, when you hit the heavy workload and CPU gets 100% busy, this additional capacity that is added will be used to resolve congestion and not to fully adapt the additional workload. This is why it is so important to act fast. Or if you know you will have increased workload, to add capacity prior to the peaks. And we do see that quite often that people have additional capacity. They have some spare capacity, either capacity on demand or CPU. But when it comes to decision to take, the decisions are taken slow. So, we have some increased workload. My phone is ringing. I'm ringing my boss. My boss is not replying. And, I cannot take decision to add one more CPU, right? That very often happens, right? And when the decision is taken, it's a bit late already, right? And then I start adding the capacity and I do it, let's say, by hand, right? So we have two problems here. First is lack of pre-approved capacity, and the second is lack of automation. So the key things to take from here is that everyone should automate adding pre-approved capacity at the first sign of the problems. And we do know customers who are doing this, and we do know customers who are not doing this, and they pay the price too. So here is the one example from one customer. So what is wrong here? We have here defined so-called soft capping. Soft capping is the way to cap our CPU capacity by defining MSU that we don't want to exceed during our 4 hours rolling average. What this means, I mean, majority of the customers still are paying 4 hours rolling average license, monthly license fee, which means that as soon as they exceed some MSU, they pay the price for this at this level, right? So some customers are running with defined MSU, which means I don't want to exceed certain amount of money that I pay to IBM, that I pay to vendors. So how does it work? I said it's a soft capping, so it was defined at 2,500, which is this line red here. But the actual MSU is this blue one, right? So after midnight, we have exceeded this MSU because this is a soft capping, right? And we have eaten a lot of CPU here, right? So in the next period, which is coming, we have to lower down the actual MSU. We have to cap the machine, not to allow to exceed those 2,500 in our 4 hours period. So this machine was capped here from 1 a.m. till 5 a.m., let's say. And then the workload has grown again, right? It has exceeded the defined MSU. It has exceeded it here twice. And then we see here is about 7 a.m. or 8 a.m. The online day is starting. And what is happening to our machine? Our machine is capped here because we already used the MSU that we defined, that we used it for previous workload, right? So at 7:30 a.m., this machine was capped. There was limited workload running because of capping, right? And guess what happened, right? The phones start ringing, right? And the customer decided to increase the workload. But it didn't help much because the increase was just tiny comparing to this workload. So it didn't fit. Basically, it was not enough, right? So they have increased the defined MSU to, let's say, 3,500 right here. And that was enough for this machine to, survive the online day, right? But notice the time here. Here we have 8 a.m. And here in this time, we have 10 a.m., right? So it took customer 2 hours to, to add some capacity, to change the defined MSU, right? 2 hours decision time. So that's a lot. That's a, very, very, very long time in an online day, right? So 2 steps and 2 hours to resolve this problem, right? Quite bad. Okay. So when I started to talk about CPU capacity, I need also to talk a little bit about the vertical high, vertical medium, vertical low, hyper dispatch in general, and logical CPs. With hyper dispatch equals to yes, we can share processors the smart way, depending on the defined weight for the LPAR and depending on how many logical processors we have. In short, vertical highs means that it's one-to-one mapping with the full general CP. Vertical medium is the guaranteed percentage share of the full general CP, and vertical low has no guarantee of any share, but it has flexibility to adopt some juice from other CPs or to move between the LPARs if there is unused capacity of one LPAR and high CPU demand on the other LPAR, that this vertical low can be varied off and on by Prism accordingly. So the rules are you should have so many logical processors that you can fully map to defined processor weight. And I will explain it on the examples as well later on. And you can have few more logical processors to become vertical low, so they can be used to adopt some additional workload when the other LPARs are not being used. You should avoid cross-door recipes, meaning one LPAR should be limited to general CPs that are in one hardware drawer. If you have CPs across multiple drawers, there will be some penalty because the context switch costs a lot. They are basically farther down. And in the last study that we had, one of the customers has one CP that was in the second drawer, and actually it turns out that the, let's say, performance of the CP was like 70% of the full GCP that they would have in the first drawer. So the performance was really degraded. Okay, so what is wrong here? This customer had just 4 GCPs available on the keg, and they defined only 4 logical processors. As you can see, they had the weight for the production LPAR about 91% of the full capacity of the keg, right? But they only had 4 general CPs and 4 logical processors. So how the HMC or how the Prism was able to divide and conquer here, right? Since we only had 4 GCPs, we had to assign 1 general CP to those LPARs that has really low weight, right? But still we had to assign the physical, vertical, medium processors, right? So those 2 were kind of assigned to those test and Q&A LPARs. And the other ones that we have spare left were only 2 vertical high, right? So instead of having 91% here of the capacity of the machine, which was 4 CPs, we only have 2. So that was kind of wasted, right? That was kind of misconfiguration because this customer only had 4 logical processors, so they cannot map fully to reflect this 91%. So actually this customer has wasted at least more than 1 general CP, right? So what can we do about this? What can we do about the situation, right? There are several ways. First, we add 2 more logical CPs. If we added 2 more logical CPs, then we have this additional vertical medium and additional vertical high. So in fact, here we can guarantee that is really 91% of what we wanted, right? So just by adding logical CPs, vertical lows, or well, logical CPs more than the physicals that we had, we can now fully map to the weight of the keg, right? Earlier we were not able, right? Because we had only 4 CPs and let's say 3 LPARs that needs the process to be assigned, right? Now it's better, right? Because we can reflect it really, really good. Can it be any better? Yes, it can. Because if we add more logical CPs, then some of our logical CPs will become vertical low. And vertical low can be switched between the LPARs. So if those 2 LPARs, this TST1 and Q&A1, will not be busy and the production one will be busy, then we will use those vertical lows to transfer the power, transfer those CPs to our high demanding LPAR. In this configuration, it won't be possible, right? In this configuration, yes, it is, right? So basically, we should assign so many logical processors that we can match the weight, plus we should assign 1 or 2 vertical lows or additional logical processors just in case that we want to use the capacity of those low utilized LPARs, right? Okay, any questions on the chat, Colin, maybe to this?
No questions just yet.
Okay, so I move further then. CPU capacity, another catch about machine scalability. MSU does not scale linearly with numbers of processors. And the more processors we have, this curve is flatter. Actually, it's not seen here much, right? Because we only have few processors. But if you see the picture of more processors, it's more noticeable, right? Basically, this linear line, which we have between 1 and, let's say, 5 processors, is not more linear here, right? When we move further in the architecture and we have more processors. So you can't assume that machine with twice as much general CPs will run twice as faster. No, likely not. No way, right? Okay, now let's go to the zip capacity. So a few facts about the zips. So zips were or are IBM response to changing world and processors getting cheaper in distributed world and open source world. As you know, in mainframe we pay for CPU seconds that we use in general CPs. And the zips processors are one-time charge, meaning that we pay only once. They have few limitations, of course. They can mainly be used by distributed workload or the new workload like Java, right? The good news is that the usage of the zips is being also allowed for the other workloads, like for example in Db2 utilities, or some or most of the Db2 engines agents inside DBM1 or master are using SRBs that are using also zips. Or recently also we added some Kix Liberty or WebSphere Liberty services to this, or REST API and so on, right? So the zips are good, zips are cheap. The problem happens when zips get busy. When zips gets 100% busy, it can spill over and use general CP. When this setting is on, which is a default, when the zips get busy, it will spill over, it will use general CP. So again, instead of using the zips, we are using the CPU cycles from general CP, and we pay for this real license money, right? Okay, here's the list of the what is being how zips are utilized in Db2 and also in non-Db2 workload. I won't list it here just for the reference. So how hot zip can be run depends on the count of the processors, right? If you have less zips, then can be utilized less. If you have more zips, then can reach more utilization without danger of the spillover to general CP. One recommendation for DB2 is to have at least one vertically high zip. Why is that? As I said, if zip is too busy, he may ask for help to general CP. He may spill over to general CP. But we had the situation in the past, like five years ago, when customer had defined vertical medium for the Db2 LPAR, and this vertical medium zip was so busy that it even didn't have the power to call for help, to say, I need help from general CP, right? That's why from this time we have this recommendation that for Db2 LPARs, there should be at least one vertical high, so it has the power to call for help, right? So zip capacity planning should be treated the same way as CPU planning capacity, because in the zips processor, we also, play the crucial workload, right? We are running also the crucial workload, DDF, for example, right? Or Db2 agents, right? So if there is some capacity lag and we cannot afford to buy a new zip, it may help if we turn off the multi-threading option for the zips, right? There are some RMF fields that can help you evaluate this. There is also a tool by IBM, which is ZPCR, which provides some estimation if this multi-threading can help. But the best is just to test it on the representative workload on representative member, Db2 member, for example, if this read can help. Okay, so I already talked about offloading to general CP. So the real driver for the capacity of the zip is how much we offload, because this is what we care. Because we don't care if zip is busy or not, because we paid only once, but what we care is if the zip spilled over to general CP, for which we have to pay the money, right? The CPU seconds, right? For example, if you are almost always offloading to general CP, then it would make sense to purchase a zip, right? As in the long term, it's cheaper to pay once for zip than the license charges for the general CP, right? So metric to be watched is basically zip offload. And in RMF, there is parameter that describes this. This is the value with the cryptic name, application percentage, IIPCP is the metric to be watched. This is saying how many times or what's the percentage of GCP that was used to help the zip, let's say, right? How quick the offload will happen is controlled by another parameter in the paramlib. The default is 3.2 milliseconds. We won't offload to general CP for discretionary workload, for discretionary service classes. Won't offload at all, which means that we will be waiting for the zips to be available. So that's why we don't advise for Db2 workload using service classes that are discretionary, because if they get stuck, right? They won't be calling for any help. They will basically be waiting for zips to be available again. The same applies for the service classes which are defined with IP owner priority to no on the service class level. They won't get offloaded to GNLCP. Again, for Db2, we don't recommend it at all. And here is some picture to understand about the few facts about the offload. So we are seeing here this customer was running the zip. This zip capacity maximum is here, and he was almost touching it, right? Once maybe, right? But regardless, he was touching it once. We see the offload here. It's happening, let's say, maybe not regularly, but from time to time, right? So why is there? We see that it never reached 100%. So why there is an offload, right? So I will maybe explain it on the next slides. So first of all, there is nothing like 70% busy or 50% busy processor, right? The processor, regardless if it's zip or just normal processor, can be either busy or not. Can be either 100% busy, something is running, or something is not running at all, right? So depending on how many working slices we have in the period, it is calculated by our utilization. So an example here, this average zip utilization was 55, but we do see that this zip is 100% busy here, 0% busy here, right? 100% busy here, again, 0% busy here, right? And so on, right? So on average, we really have 55%. But 55 means that there is 55% of the periods when the processor was 100% busy. And what happens when the processor is busy at 100%, especially zip? Then we may call for help to GNLCP after a period of 3 milliseconds. So we don't call for help here because this period was quite short, but we do call for help here, right? When zips get busy, and it's busy for a long time, 3.2 milliseconds, then we offload to GNLCP. So those periods where those GNLCP were used, right? That's why here, right, we had those zips were 70% busy. 70% means that 70% of the time, the processor was busy at 100%. That's why we have this offload here, right? So this is the thing to remember. So zip busy utilization tells us nothing. We don't care actually about this one. What we care is about money that we spend on GNLCP when we do the offload. Okay, CPU capacity. So what is wrong here? Let's assume that those all LPARs here are Db2 LPARs, right? I already mentioned that Db2 LPARs should have at least one vertical high dedicated for the LPAR. Those guys, if they were production Db2 LPARs, they will not be able to call for help to GNLCP, right? Because they only have assignments of vertical medium, which can be shared, which is not dedicated to the partition. So if we see such a picture for the customer, we say, you may be in trouble when you get busy, right? You won't be able to get to help of GNLCP. Okay, let's move to capacity. Memory real storage. Again, memory is one-time charge. You buy it and you have it. And memory is the cheapest trade-off for performance. And we often see the customers who are running, to the edge of the memory, to memory full with paging. Or even if not paging yet, they are dangerously close. And what dangerously close means? Dangerously close means lower than the max space setting for the dump. When any other space take a dump because of the, I don't know, Db2 bug or some other events, it needs to pull out the working memory and write it to DASD. This happens in real memory. And when real is exceeded, we page to auxiliary. And actually, when we page to auxiliary, that's the bad thing because it's slow, right? But actually, it also can take LPAR out, right? When we run out of auxiliary, right? So the problem with this is that we often see installations where Db2 admin do not know how they use the memory, or they do not know how much memory they have on the machine. Maybe they have even more than they were given, right? Because, for example, MVS guys do not give it to him or do not want to share, right? And this is quite often, actually. We have seen in last, I don't know, 5 studies that we made in the last year, 4 of them has memory that was not assigned to the developer. That was basically bought from IBM. It was not used at all. And the bigger memory means better overall efficiency, right? We can allocate bigger buffer pools, we can page fix them, we can use reals allocate, we can use FTBs, which are in memory non-leaf pages, kind of cache, and other features that speeds up Db2. So by not allocating enough memory, we are wasting performance opportunities for Db2. So the minimal recommendation would be to have at least as much free of real memory as your max space setting for the dump. And also you need to monitor for paging, right? Another recommendation is to make sure that aux management is on for your dumps. Aux management will stop the dump, so writing the dump when there is excessive paging on the system, right? And the dump capture should be pretty quick. And if we are really paging to auxiliary, it's really slow. So normally in the well-tuned system, when there is enough real, taking a dump should be less than 10 seconds, should be 5 seconds, maybe 12, right? Maybe 3, right? But I know also the customers who are terribly afraid of taking the dump because they know they don't have enough real memory and they will be always paging. And when we page, when Db2 is taking a dump, the address spaces are basically frozen because we are synchronously pulling the memory and writing to the DASD. And when we do it through the aux, then it basically slows down, right? Even more. Okay, so here's the example of the customer who has the max space set to 51 megabytes, and the real available was about 40. So what would happen if they take the dump, let's say here, right? Then they will start to page, right? And this is the dangerous situation that we would like to avoid. We don't want to see the pictures like this. Always make sure that you have more real than the max space that you have defined for the dumps. And again, I also already mentioned this customer had enough memory to cover for real, to be really on the safe side of this picture, but it was basically not assigned. How does it happen? This is a trivial thing because it happened during the upgrade for the hardware. They upgraded the hardware, they buy a new Z16 machine, but no one took care of the memory. No one assigned more memory that was available. So trivial thing that can be easily repaired. For the memory capacity, right? Here we see the example that we also don't want to see. We see the paging in Db2 address spaces. So this Db2 was paged out. We didn't have enough real storage, and we got paged out to auxiliary. Again, that's another customer. Memory was available, but what was basically not assigned again, right? That's another spectrum of the capacity, but that's capacity for the memory below 30-bit addressing space, which is actually nothing that we can do, right? Because we have the range that is basically limited, right? But just another aspect of capacity planning, memory for the common storage, let's say. There are hard limits, but we can see this user was having the steady numbers of the threads here, this line, and then it started to grow, right? And here we have the numbers of threads. It started to grow here, everything was fine, and here is the number of available ECSA, right, in total. It started to grow here, to grow. Then it grew to 2000, and we see significant use of the ECSA for Db2. And here again, it started to grow. And then it hit the limit of the C thread, let's say almost. of 4,000, and here is where Db2 has abandoned. We didn't have enough ECSA to adopt 4,000 threads in the same time. So this is nothing about capacity, but this is about capacity, how much you can afford to run in your Db2, how many threads you can run in your Db2, what is your storage footprint, right? For the particular workload, right? So customer hit the limit and Db2 actually abandoned, right? In this case, allowing 4,000 threads was not realistic. It should be lowered by the zparm or guarded with Db2 system profiles. Okay, in Db2 itself, we have the control of use of the real memory in Db2. It's controlled in version 12 by real storage management zparm setting, which can be off, on, or auto. When you have plenty of real memory, this zparm should be set to off, and all Db2 storage used by threads or by some structures are not freed at all for the performance, right? Otherwise, it should be auto. What auto is trying to do is to balance between how much can be used and what can be discarded, right? So this is kind of short explanation what auto is doing. There are some more details here, which I will not talk about. In version 12, we have changed the auto behavior now. And now how it works, it actually works even smarter. So now the new auto behaves like a off till it reaches the max space for the dump, till it reaches 1.2% size of the max space, right? And when it reaches this limit, then we start discarding real memory. So it's kind of very efficient way to do this. If we have enough real, then allocate and don't discard. If we are close to the limit, if we are close to max space, then start discarding. Kind of smart. And everyone, actually this APR I think is 1 or 2 years old, so probably everyone should have it already on. In version 13, we removed this APR. Now everything is auto, right? In version 13, we also discard the memory in a different way than in version 12. In version 12, Db2 was discarding the memory, the frames, and in version 12, we let zOS to do it, which is far more efficient, let's say. Okay, in summary for the memory, you should review your memory budget and how much can allocate. And there is a list of, let's say, zparms that affects allocations of the memory in Db2. Normally, the biggest consumer are buffer pools, which can be really big nowadays. There are not really hundreds of gigabytes, but the other pools can consume also some decent amount. Like all those pools here can allocate up to 4 gigabytes or even more of the memory. So you can basically budget it into your real and see if you are over the budget or not, right? Indirectly, as I mentioned, the C thread or the maxDB thread can also affect the overall budget because it's limiting you below the 30-bit addressing line. And speaking about the buffer pools, there is a setting that allows also to page fix buffer pools in memory, preventing them to be paged out. And we do recommend it for the customers who have enough memory. But if you don't have enough memory, don't page fix the buffer pools, right? This setting can be also hardened by WLM setup. You can add to the Db2 address spaces service classes the attribute storage critical equals yes, and then kind of guaranteed that address spaces of Db2 will be the last to page out, right? One more thing about the memory I have to mention. When you are running few Db2s in one LPAR, and let's say that one Db2 is the production Db2, and the other Db2 are the test Db2s on the same LPAR. If there is a memory leak for those test Db2s, they can affect the production Db2 as well. So there is a way to protect this production DB2 by specifying another zip arm, real storage max, for those other DB2s that are less important. And you can say in this zip arm how much they can consume. And if they consume more, then they will terminate, protecting our production DB2. So this is kind of nice feature. It's not used much because most of the users are not running testing in production LPARs, but we have seen some usage of this for the few customers as well. So in summary, what you should take out of this presentation is that CPU capacity increase is non-linear in relation to CPU busy. General CPs are expensive, but bear in mind that lack of the CP is more expensive if you have an outage, when your business is slowed down or stopped. You should be careful with capping, because if you cap someone, it can cause the sympathy sickness for the others, right? You should remember that zips are cheap comparing to general CP. So the more you have, the more you offload to the zip, the more you save. However, if you have not enough zips and you offload to general CP, then it means that you still pay the real money, right? Another takeout from this presentation is that memory is the cheapest way to trade for CPU. Memory nowadays is really cheap, right? And you can save a lot of CPU by just allocating lots of memory. Don't page to aux, don't overcommit the memory. And make sure that you use the memory that you purchased. And the last advice, never waste a good outage. Never waste a good outage to improve your situation, to your capacity lags, right? That's the only thing that management takes care of is money, right? If you have outage, you are losing money, then it's really easy to understand by management that you need to purchase new CPU, a new zip, or more memory. So that was it, I think. Are there any questions, Colin, in the chat so far?
No, not that I can see. No.
Okay. So this is the session code, and I really appreciate your feedback. If I did well, or what can I improve? I really appreciate if you will be honest. I really do. If you have any questions, you can ask now, or you can also send me an email. I will be happy to answer.
Okay. Thanks very much, Mihail. That was really good. Really in depth. There's a few items I took away from that myself to investigate and check out. So it's always good to refresh on some of these, but it's also good to dig in depth too. So from the DB2 stream, oh, I should say, please remember to do the feedback. This is code 6B. There's the link there, but you can also do it from your agenda page. So that should be straightforward, and we need that feedback. The next DB2 session is actually not until 2:30 when when your swapped colleague Anthony Ciappatoni will be presenting, and he's talking about some more swap tails, in fact. So looking forward to that. That's not till 2:30. Sorry, no, it's later than that. It's actually 3 o'clock. It's the next DB2 session, 3 o'clock, and that is session 6E. Before then, we've got the lunch and learn at 12, which is unleashing strategic impact hybrid cloud in mainframe organizations. I think there's other ones available at 12 o'clock. And then, as I say, there's a gap in the DB2 stream until 3 o'clock when we're back with Anthony Ciappatoni. So in the meantime, if you've got no questions, then we'll close it there, I think. Thanks very much, Mihail. There would be a round of applause, I'm sure, if we had people in the room, but as it's virtual, consider there be a round of applause now for you. Thanks very much indeed. That was really good.
Yeah, that's the danger of being online and remote, right? You don't see the faces. You cannot say if people are happy or not. So if you're happy, let me know. If you're not happy, please let me know too. I will appreciate really.
Great. Thanks very much indeed.
Thank you.
Okay, catch everyone on the other side of lunch. Cheerio.